Welcome to lecture 43 of week 9. In this week, we are talking about simplex method for linear programming problems. In our previous lecture, we have taken an example and demonstrated the steps for simplex method. In today's lecture, we will continue our discussion on simplex methods. We will now take another example in 3 variables and 3 equations, and we will solve the problem using simplex method. So, before that, let us summarize the computation steps that we have seen already, and we are talking about a maximization problem. So, the first step towards solving a linear programming problem using simplex method is to express the problem in standard form. In standard form, all the constants will be of equality type, the right hand side constant will be non-negative, and all the decision variables are also constrained to be non-negative. In the next step, we start with an initial basic feasible solution in canonical form and set up the initial tableau. In the third step, use the inner product rule to find the relative profit coefficients, that is C j bar, for all non-basic variables. Note that for basic variables, the relative profit coefficient C j bar is always 0. If all C j bar is less or equal to 0, then the current basic feasible solution is optimal. So, when all the relative profit coefficients are less or equal to 0, then the current basic feasible solution is optimal. Otherwise, select the non-basic variable with most positive C j bar, that is relative profit coefficient, and this non-basic variable will enter the basis as basic variable. So, the non-basic variable with most positive C j bar value enters basis as basic variable. So, one basic variable has to leave the basis and will become non-basic variable. For that, we apply the minimum ratio rule to determine the basic variable that will leave the basis and become non-basic variable. Perform the pivot operations to get new tableau and new basic feasible solution. Check if the current basic feasible solution is optimal by calculating the relative profit coefficients for all non-basic variables, and go to step 4, where you check whether all the relative profit coefficients are less or equal to 0. Repeat the cycle until optimality conditions are reached, and the optimality condition for maximization problem is for all non-basic variables, the relative profit coefficient C j bar will be less or equal to 0. Now, let us take another example. A chemical manufacturing company uses 3 different raw materials A, B and C to produce 3 different products D, E and F. So, there are 3 different raw materials. Using these 3 different raw materials, 3 different products can be formed D, E and F. We are not talking about reaction kinetics here, but how much of A and how much of B and how much of C are required to produce each kg of D, E and F are given in the table. For example, for each kg of product D, 1 kg of A, 1 kg of B and 3 kg of C are required. Similarly, for E and F. This is a hypothetical situation, but we consider that these informations are true and we will formulate the optimization problem so that we can get the optimal production schedule that will maximize the daily profit. The maximum availability per day for each of the raw materials 100 kg, 150 kg, 320 kg are given. Profit per kg of D, E and F are also given. So, now let us formulate the problem. Let us consider that the production schedule is we will produce x 1 kg of D, x 2 kg of E and x 3 kg of F. Now, there are three constants on the availability of raw materials A, B and C. We are considering we will produce x 1 kg of D, x 2 kg of E and x 3 kg of F. To produce x 1 kg of D, we need x 1 kg of A. To produce x 2 kg of E, we need x 2 kg of A, and to produce x 3 kg of F, we need 4 x 3 kg of A. So, x 1 plus x 2 plus 4 x 3 must not exceed 100. So, that is the first constant that we get. Similarly, we get constants on B, which will be x 1 plus 2 x 2 plus x 3 is less or equal to 150. Similarly, 3 x 1 plus 2 x 2 plus x 3 is less or equal to 320. So, these are the three constants. So, now we have formulated the three constants. Let us write down the objective function. The objective function is to maximize the profit. So, x 1 kg of D will give 2 x 1 kg of 2 x 1 amount of profit plus 3 x 2 plus x 3 is the total amount of profit. So, z equal to 2 x 1 plus 3 x 2 plus x 3 is the objective function. We need to maximize this. So, the complete formulation now is maximize z equal to 2 x 1 plus 3 x 2 plus x 3 subject to these three inequality constants. So, now to solve this problem using simplex method, the first thing that we have to do is to express the problem in standard form. Note that there are three inequality constants. So, we have to add three slack variables. So, we have to add three slack variables S 1, S 2 and S 3 to convert this linear programming problem to this linear programming problem, which is in standard form. So, if you look at this, you see that this part helps you to start with an initial basic feasible solution. So, S 1 and S 2 and S 3 becomes basic variable, x 1, x 2, x 3 becomes non-basic variable, and you have a basic feasible solution in hand to start the initial W. So, this is what you get as W 1. So, S1, S2 and S3 are the basic variables, their cost coefficients are all 0, and x1, x2, x3 are the non-basic variables. So, you can check this, that is in canonical form, and x1, x2, x3 are non-basic variables, and the coefficients of the constants are written. This column represents the right hand side constants, which are 100, 150 and 320. Now, the first step is to compute the relative profit coefficient C j bar. We know for basic variables C j bar equal to 0. So, you can directly put 0, 0 and 0 here corresponding to basic variables S1, S2 and S3. So, C j bar is calculated using this equation, C j bar equal to C j minus sigma C b I A I j. Now, note C b I is basically the cost coefficients of basis S1, S2 and S3. So, they are all 0. So, in the first table C j bar is basically equal to C j here for the non-basic variables x1 and x2. So, that is why you get 2 and 3. Now, let us look at which C j bar is most positive, because that will enter as basic variable into the basis. So, we see that 3 is most positive. So, x2 enters basis, x2 non-basic variable will enter as basic variable. So, which basic variable will leave? For that we have to compute the ratio B I bar divided by A I S bar. So, B I bar A I bar S ratio we have to find out. So, what we do is corresponding to non-basic variable column x2, we divide Bj or Bj bar by these coefficients. So, focus your attention here, here and now look at the minimum ratio column. So, this is 100 divided by 1 is 100. This is 150 divided by 2 is 75. 320 divided by 2 is 160. So, this is how you compute minimum ratio. So, once the minimum ratio has been computed, we see that 75 is the minimum corresponding to second row. So, S2 will leave basis and X2 will enter. So, X2 enters, S2 leaves. So, the pivot row is row number 2 and the pivot element is circled, which is 2 here. You see that X2 has replaced S2. So, now we have to perform elementary row operations, so that we have 1 here and 0 elsewhere in this column, so that you have the canonical form. So, this can be obtained by multiplying the second row by half. For this first column, you have to perform, for this first row, you have to perform first row plus minus half into second row. And for this, you have to add to this third row the second row multiplied by minus 1. So, once you do this, you will have 1 here and 0 in these two places. So, this is what you will get in tableau 2. Note, we have 1 here and 0 elsewhere in the column. Next, we compute Cj bar. Note that you are also performing the elementary operations on these column for constant. So, you find out Cj bar now for each of these non-basic variables. So, what are the non-basic variables? x1, x3 and s2. Cj bar for basic variables x2, s1 and s3 are all set 0. So, using this formula, we compute Cj bar. So, Cj bar can be computed as Cj. So, let us find out for non-basic variable x1. So, this is 2, which is Cj, minus Cbi Aij. So, 0 into half plus 3 into half plus 0 into 2. So, this is what this equation represents. So, this is basically 2 minus 3 by 2, which is equal to half. So, this is half. So, this is how you compute Cj bar for non-basic variable x 3 as well as S 2. Now, you see that the most positive Cj bar is half, which corresponds to non-basic variable x 1. So, x 1 will enter basis. So, which basic variable will leave? For that we compute the ratio B I bar divided by A I S bar. So, for that we take the divisions 25 by half is 50, 75 by half is 150, 170 divided by 2 is 85. So, minimum is 50. So, S 1 leaves basis. So, S 1 leaves, and in place of S 1 x 1 enters. So, this has been shown now, x 1 has entered basis and S 1 has left. So, the pivot row is row number 1, and the pivot element is half, which has been circled in red. So, again we perform elementary row operations, so that we get 1 here, 0 here and 0 here. So, this can be obtained by multiplying the first row by 2, by performing R 2 plus R 1 into minus 1, that means R 2 minus R 1 will get this, and by performing R 3 minus 4 R 2 you can make 0 here. So, once you do this, you will get the third W as shown. Note here 1 0 0. So, again we compute Cj bar following this equation, and we now find that all Cj bar are less or equal to 0. There is no Cj bar which is positive or greater than 0. All Cj bar less or equal to 0. So, we have reached optimality conditions. And at optimal condition, the basic variable x 1 is 50, the basic variable x 2 is 50. Non-basic basic variable S 3, which is slack variable, is 70, but this does not participate in the computation of objective function z. So, the profit is 2x1 plus 3x2 plus x3, x3 is 0 because x3 is non-basic variable at the optimal final tableau. So, profit is computed as 250. So, the production schedule is that we produce 50 kg of D per day, 50 kg of E per day, but do not produce any F. According to the data shown or whatever data we have considered, the optimal daily production schedule is 50 kg of D and 50 kg of E, no F. That will maximize the profit. Note that this optimal production schedule may change if we change the cost coefficients in the objective function. So, now let us give geometric interpretation to this simplex method. The simplex method is based on the same geometrical consideration as the graphical method. This can be seen by looking at a problem that can be readily solved by both the methods. So, if I take a two variable problem in two equations, this can be easily solved using graphical solution method. We can also solve that using simplex method. Then we will be able to demonstrate that the simplex method is based on the same geometrical considerations as the graphical method. So, consider the problem shown, a simple linear programming problem in two variable and two constants. So, we can obtain the solution using graphical method, and the solution is obtained as x1 equal to 8, y equal to x2 equal to 3, x1 equal to 8, x2 equal to 3. So, look at the corner points 0 0, which is the origin, one corner point of the feasible space is shaded in blue, 0 7 is another corner point, 12 0 is another corner point, and 8 3 is another corner point, and 8 3 happens to be optimal solution. Now, if I solve the same problem using simplex method, I will introduce two slack variables here, S1 and S2, so that the inequality constants become equality constants, and S1 and S2 will be considered as basic variable, x1 and x2 will be non-basic variables. So, starting basic feasible solution will be x1 equal to 0, x2 equal to 0, which is origin. So, from there you will go to this corner point, and from this corner point you will come to this. That means, the initial table you will have this as basic feasible solution. In the next tableau you will have this basic feasible solution, and in the final tableau or the third tableau you will have 8 3 as the basic feasible solution. So, basically the simplex method provides a means of moving from one basic feasible solution to another until we reach the optimal value of the objective function. So, simplex method is an efficient way of moving from one basic feasible solution to another until we reach the optimal value of the objective function. And the basic feasible solutions are always corner points of the feasible region. So, with this we stop our lecture 43 here.